Yeah, good morning, everyone. Yeah, this is Dr. S. Venkateswarlu, working as a professor of ECE at IARE, Hyderabad. Yeah, today we will discussing about windowing characteristics and Windows. We know that all Windows basically by for designing finite impulse response filters, we require that Windows. So using this all windows like Anning, and Kaiser window. So, what are the major characteristics? What things are required for designing uh, non-recursive filters? For this case, fundamental trade-off between main lobe width and side lobe amplitudes. So, as window smoother, so peak side lobe decreases. We will expect that what do you call window smoother, that peak side lobes decreases. If it is increases, we are unable to expect that smoother. Okay, that's the main characteristics. But the main lobe width is increases. This is the interlink with this side lobe and main lobes. So side lobes are decreases, main lobes width increases. This is the major characteristics while we are using the windowed or windowing techniques. Okay, need to increase window length to achieve the same transition bandwidth. Okay, so specific necessary for windowing design method. There is a specific necessary for the while you are using that Hamming or Hanning or Kaiser or Blockman windows. So there is a specific specification necessary for window design methodologies. Here it is signed that where omega c, in terms of that omega c, where cutoff frequency. Okay, that h is the what you call h and t power j omega, the delta maximum passband, and desired frequency responses is d into sd into e power j omega. Okay, so here the width delta, what the this width, okay, like this, the width is delta omega, that is transition band. Okay, where within this what you call this width is delta omega m. The delta omega m, it is what do you call this width is, so width of the window main lobe. Okay, width of main lobe. Okay, so like this should follow that all, where sd of delta of omega and desired frequency response is d power j omega. This is the specification necessary for windowing design aspects. So you should follow this all. Okay, here and what do you call delta? The delta values are is also specified positive or negative. If it is delta is the maximum passband ripple, where omega c, that omega c is where this omega c is assigned vertical cutoff frequency. Like this, by using this all specified what you call parameters or vertical width of each and every characteristics values. This is the specification for windowing window design method. If you are using the Kaiser window or Hamming or Hanning and Blockman and so on, okay, we should follow this all specification for window design methodologies. Okay, a response must not enter the shades region, but so using this all that specification, there is a, you have to follow that all key properties, that 3 or 4 like this. So now we are concentrating that key property 1 of the window design method. So here the window design method, we should follow this same specification. It is specified. So that particular property, the property 1 is equal transition bandwidth on both sides of the ideal cutoff frequency. Okay, it is specified. Next, key property 2 of the window design method. So here using this all, so that the property number 2, peak approximation error in the passband, delta is equal to that in the stop band. Okay, like this it is specified. Next, coming to third property, these are the key property number 3 of the window design method. Here it is specified the properties are involved. The property number 3, distance between the approximation error peaks, okay, is approximately equal to the width of the main lobe. What do you call that? Delta omega. Yeah, like this it is specified here. Okay, in terms of this. Okay, next, coming to the next key property 4 of the window design method. The property is followed by the width of the what you call main lobe is wider than the transition bandwidth. Okay, so like this, here is you can verify that what you call delta omega width and delta omega m. Okay, like this you should follow these all properties. These all properties are depending upon specification. It is specified specification of the windowing design methodologies. Next, coming to the key property 5 of the window design method. Here also it is specified. Property number 5. Peak approximation error is determined by the window shape. Okay, that window shape is independent of the filter order. The filter order is specified what you call either N or maybe M. Okay, so using this all value, the peak approximation error is determined by the window shape independent of the filter order. Okay, so using this order, it is either it is independent or dependent. So you can decide based on that. The property is useful. Peak approximation error is determined by the window shape independent of the filter order. Okay. Next, coming to this passband stopband ripples. Yeah, passband stopband ripples are often expressed in decibels. We know that one. Passband ripple is 20 log base 10 of into 1 plus delta p into in terms of the decibels. Or we can consider that a peak to peak passband ripple is approximately 20 log base 10 1 plus 2 plus 1 plus 2 delta p. Yeah, minimum stopband attenuation is minus 20 log base 10 delta s into dB. This is the what you call the specified value. It is a desirable. So use this a simple example where delta p is equal to 6%. We can consider that a peak to peak passband ripple is approximately equal to 20 log base 10 1 plus 2 into delta p. It is also equal to what you call 1 decibel. So like this, if it is delta s is equal to 0.01, so minimum stopband attenuation is equal to minus 20 log base 10 delta s. It is also equal to 40 decibels. So the band edge frequencies like omega s and omega p are often called corner frequencies. So particularly when they are associated with a specified gain or attenuation, say for example gain is minus 3 decibel for a decade. So for this the passband stopband ripple are often expressed in terms of the decibels. Yeah, this is the summary of windowing design procedures. Like one is ideal frequency response has infinite impulse response. Yeah, second procedure is to be implemented in a practice, it has to be truncated. We know that all truncated background and so on. Shifted to the right to make is causal or casual. Yeah, coming to third procedure, truncation is just pre-multiplication by a rectangular window. Using the tall window, how it is truncated, already we have seen. We have done that case. The filter of the large order as a narrow transition band. Okay. However, so sharp discontinuity results in side lobe interference. Okay. That side lobe interference independent of the filter's order and shape, what you call Gibbs phenomenon. Okay, so windows with no abrupt discontinuities can be used to reduce Gibbs phenomena oscillations. Okay, so that's why we should follow this all procedure step by step. Of that, we will expect our design resultant without any error. Okay, like using this all windows. These are the popular windows. One is Hanning and Hamming, Blockman. Okay. Next, advantages, disadvantages of the windowing technique. What are the major merit and demerit while you are using the windowing node or window techniques? Either we are using the Hanning window or a Hamming or Kaiser or Blockman windows. What are the major advantages and disadvantages while you are using this type of technique? It is a simple method to implement to get the desired response. So we are setting that our desired response. Once we are entering that all, while you are using this windowing techniques or windowing methodologies, we will expect that all less errors. We will expect that all windowing response is expected shape or whatever it is. That is your desired response. That's why while this is the major merit, it is a simple method to implement to get desired response. It does not have much flexibility as there are an equal amount of passband and stopband ripples. That passband and stopband ripples presents in the response that limits the ability of the designer to make the output more ideal. So, like this, using this much, if somewhat it is not up to the mark, like not that much flexibility because of the equal amount of passband and stopband ripples present in the response. That limits the ability of the designer to make the output more ideal. So there is a minimum computation involved in executing this technique. Note that involvement of this, no matter how much we increase the value of m, go on increasing or decreasing, what happens? It is so that's why somewhat it is major merit. Yeah, the maximum magnitude of the ripple is fixed, except when using the Kaiser window. Remaining all are Hamming or Hanning and Blackman windows and so on. The maximum magnitude of the ripple is fixed other than this Kaiser window. Okay, so due to this convolution of the desired frequency response and the spectrum of the windowing function, it will appear. So like it is not possible to find out the specific values of the passband and stop band frequencies. This is the major merit while you are using windowing technique. What is demerit? When the filter order that is followed by M is increased, this leads to an narrow frequency response in which the smoothing is reduced. Okay, so this leads the big side lobes that are coupled with the lower transition weight, which is Gibbs phenomena that was previously mentioned or we have seen using that all side lobes and main lobes. The side lobes are increases, main lobes of it is varies. Because the main lobes are increases, how many side lobes are increasing or decreasing? Yeah, this leads to big side lobes that are coupled with a lower lower transition width, which is Gibbs phenomenon that was previously we have done with the best examples. However, the Blackman Paris window helps to reduce the effects of Gibbs phenomena, but not up to the mark because of that Gibbs phenomena and keep it is to the minimum. It's not maximize our desirability. Okay. Yeah, steps for solving the problem using the windowing methods. So all numerical problems and all how we are solving using the graphically or mathematical notation. Here we should follow. Let us look at the how to utilize these functions that we have learned about this problem. Okay, using this all simple way or methodologies or procedure or steps, is you can solve these numerical problems. because of in the practical aspects we require this type of numerical problems and solution. Usually can design our finite impulse response non-recursive filter. First, let us to go through the steps to solve the problem related to the windowing method of non-recursive filter, that is finite impulse response filter. Now, step 1, find out h of omega, and omega c into h of omega is equal to e power minus j alpha omega. This is the first step. Consider this first step. We should follow this measure 1. Under this, the equation can be given directly in the equation. The values of m can be given and we have to calculate alpha. Okay, if it is they are ready to provide that small n value or maybe capital N value, the value of the m can be given and we have to calculate the alpha is equal to m minus 1 by 2. The phase delay is given, the values of alpha with which you can find out h of omega. So like this value can be given directly, and the cutoff frequency followed by fc can be given with which we have to find omega c is equal to 2 pi into fc. Okay, the sampling frequency, it is followed by fs, can be given with which you have to find omega c is equal to 2 pi into fc by fs. Here fs is given and fc also given. You can calculate that what we call omega c. Okay, like this we have to follow this all step by step procedure. First step, it is very crucial for finding this all h of omega and omega c into h of omega is also equal to e power minus j alpha into omega. Other thing is it is independent with this alpha it is m value, where alpha is equal to m minus 1 by 2. Yeah, coming to the second step, now you find the value of h of n, that impulse response of the what you call non-recursive filter or impulse response of the recursive filter, infinite impulse response filter, response by taking the inverse discrete Fourier transform of h of omega less than p, okay, what you call greater than takes h of that impulse response is equal to 1 by 2 pi integral minus pi to pi h into omega e power j omega n into d omega. So like this, using this, if you consider the type for low pass filter, h of n is equal to 1 by pi of n minus alpha into sine into n minus alpha into omega c. Okay, for using that low pass filter. Yeah, coming to the high pass filter, where h of n, that impulse response is equal to minus 1 by pi of pi into n minus a sine of n minus alpha into what you call omega c. So however, when small n is equal to what you call alpha, how it is varies. If you are having that n is equal to alpha, the time h of alpha is equal to 1 by 2 pi integral pi by that minus pi by 2 integral minus pi 2 plus pi, okay, the d omega into e power minus j what you call alpha omega into e power j alpha omega. Like that, when small n is equal to alpha, try to calculate that h of alpha, where h of alpha is equal to like this, we should follow. Hence the integral term will be cancelled off if you are following like this. Next step. Step number 3. Now we have to identify the windowing function based on what window you are using. As you see from the table, as per this table, if you are in the different windows, okay, substitute the values of n into the function of to get the coefficients pertaining to the window function. We can form a table similar to the one below. For better understanding, you can follow this table. So value of n is, if the n is equal to 0, okay, desired frequency response, that is SDR, that is the desired frequency SD, H into D, where D is the desired, n value is, that means HD SD of n, that n value is substituted, where n is 0. The time windowing function is, that is followed by W of n, that is n is substituted 0. The time, or the function after the performing the windowing method, where h of n is equal to sd of n into w of n. Like this, where I calculate that impulse response. If it is n equal to 0, h, that n equal to 0, h of 0 is equal to sd of 0 into omega 0, and so on, like where n is equal to 1, 2, 3, 4, and so on, minus 1. Like this, how it is a vary that desired frequency response in terms of the g of n. After that, the windowing function w of n will be verified. Okay, after that we will ready to verify that function after the performing windowing method. It is followed by h of n is equal to that h of n, what do you call that, h of n is equal to, what do you call that, omega n into r into, what do you call, desired impulse response. Okay, so like this, if it is up to m minus 1, the time of the windowing function and desired frequency function after the performing the windowing method is, you can evaluate under step number 3. So first of all, we have to identify the windowing function based on what window you are using. Okay, as you see that using this all graphical tabular form, substitute the values of n into the functions to get coefficients pertaining to the window function. You can form the table like this, as you can observe. Third, step number 3. Coming to the fourth step, now we have to find the final equation after the windowing technique has been applied. For to identify which of the values from the table above should be included. You need to solve this equation and substitute the, what you call, respective value from the table. We have seen that our previous table. Okay, so you can calculate that h and t power j omega. So simplify and solving this equation will give you the final transfer function. After finishing this step number 4, we will expect that our final transfer function. The final transfer function, after that we go for step number 5. We are not done just yet. We have to transform this final equation using the Z transform into the Z domain. Like this, you should follow these 5 steps. Okay. This is the summary key properties of windowing design method. Like the equal transition bandwidth on both sides of the ideal cutoff frequency. We are equal peak approximation error in the passband and stopband. Third one is distance between approximation error peaks is approximately equal to the width of the window main lobe. And fourth one is the width of the main lobe is wider than the transition band. After that, so the peak approximation error is determined by the window shape. It is independent of the filter order. Okay, we will expect here approximation error peaks. Here by using this all what you call graphical representation, equal transition band on both sides of the ideal cutoff frequency. Okay, that equal approximation error peaks is observed, and h into e power j omega, and desired frequency response is d into e power j omega. Like this, it is observed. Where delta omega, the transition bandwidth, and the main lobe width, delta omega m. Okay, width of the main lobe is wider than the transition band, and the peak approximation error is determined by the windowing shape independent of the what you call filter order or order of the filter. Yeah, the summary of the windowed finite impulse response digital filter design procedure. Here we have to select the suitable window function, specify an ideal response SD of omega. Third one, compute the coefficients of the ideal filter SD of n. And fourth one is multiply the ideal coefficients by the window function to give the filter coefficients. Fifth one, evaluate the frequency response of the resulting filter and iterate if the necessary or typical. It means the increase capital M. If it is decreasing, what happens? If it is increasing, you usually can observe using the different windowing technique. Okay, if the constraints we have been given have not been satisfied by with reference to evaluate the frequency response of the resulting filter. The typical value, it means that M is increasing and decreasing, or the specified ideal response and coefficients for the ideal filter with the desired frequency impulse response. Like this, we have to observe while you are using the windowed finite impulse response filter design procedure. Yeah, coming to this finite impulse response non-recursive filter design using the windows. FIR filter design based on the window is simple and robust. However, it is not optimal. But we will expect that optimal. But while we are using this windowing technique, we are unable to expect the optimal. The time we go for the further, like using Remez approximation, MCLR, and so on. Yeah, the resulting passband and stopband parameters are equal, even though often the specification is more strict in the stopband than the passband. Unnecessary accuracy in the passband. Next, ripple of the window is not uniform. Like we can specify decays as we move away from the discontinuities points according to the side lobe pattern of the window. Yeah, just now we have seen that how it is the omega delta, delta and delta m and delta. Okay, these all values. Okay, so by allowing the more freedom in the ripple behavior, ripples are either maybe increasing or decreasing. Okay, so we may be able to reduce filters order, hence it is complexity. Okay, if it go on increasing or decreasing, user can evaluate. Okay, now coming to this Parks-McClellan filter design algorithm. Why we have chosen this one? Because of that FIR filter. That FIR filter is we are not optimized. We are not observed optimized. We have to consider that Parks-McClellan filter design algorithm. Yeah, the Parks-McClellan algorithm published by James M.C. Clellan and Thomas Parks in 1972 is an iterative algorithm for finding the optimal Chebyshev filter impulse response filter or non-recursive filter. This is the background of Parks-McClellan filter design algorithm. The Parks-McClellan algorithm is utilized to design and implement efficient and optimal FIR filter. But while they are using that non-recursive filter like FIR filter, by using the windowing technique, we are unable to receive the optimum responses. That's why we have chosen this Parks-McClellan filter design algorithm. The Parks-McClellan algorithm is utilized to design and implement efficient and optimal finite impulse response filters. Yeah, it uses an indirect method for finding the optimal filter coefficients. Okay, like this. The goal of the algorithm is to minimize the error. This is the major task. Why they are using the Parks-McClellan filter design and algorithm? The goal of the algorithm is to minimize the error in the passband and stop bands by utilizing the Sabishu approximation. Okay, that's the main significance while you are choosing this particular optimum filter. Okay, the Parks-McClellan algorithm is a variation of the Remez exchange. Remez exchange algorithm. Here, with the change that it is specifically designed for finite impulse response filter or non-recursive filters. Okay, so it has become a standard method for non-recursive filter like finite impulse response digital filter design. That is the significance and importance of Parks-McClellan filter design algorithm. Okay, so passband and stop bands of a filter design by the Parks-McClellan algorithm. The y-axis is the frequency response. You have to specify that all. If it is x-axis and y-axis, that y-axis is what you call y-axis is the frequency response h of omega, and the x-axis are the various radian frequencies omega I. It can be noted that the two frequencies marked on the x-axis, omega p and omega s, where omega p indicates the passband cutoff frequency and omega s indicates the stop band cutoff frequency. So the ripple plot on the upper left is the passband ripple, and ripple on the bottom right is the stop band ripple. So by using the graphical response, you can understand this all, how it is varies. Yeah, the two dashed lines here, it is observed that what you call here it is specified, where the ripple plot on the upper left is the passband ripple, and the ripple on the bottom right is the stop band ripple. Yeah, the two dashed, we have verified that all either dashed lines here and here and here and like this, where the two dashed lines on the top left so of the graph indicates that delta p. Okay, and the two dashed lines on the bottom right indicates the delta s. Okay, so all other frequencies listed indicate the extremely frequency of the frequency response plot. So as a result, there are 6 extreme frequencies, and then we add the passband and stop band frequencies to give the total 8 extreme frequencies on the plot. Yeah. Okay, like omega s, omega 3, 4, 5, 6, and so on. Okay, like this we will expect that all optimum, the passband and stop bands of the filter design by the Parks-McClellan. The y-axis is the frequency response h of omega, and x-axis are the various radian frequency omega I, where I is here it is substituted 1, 2, 3, and so on. Where here is I is 1, 2, 3, here it is 3, 4, 5, 6. Okay, like this, passband and stop bands of a filter designed by the Parks-McClellan algorithm. The y-axis is the frequency response h of omega, and the x-axis are the various radian frequencies omega I. It can be noted that two frequencies marked on the x-axis, just now we have seen with reference to the graphical response, omega p and omega s. Omega p indicates that the passband cutoff frequency, omega s indicates the stop band cutoff frequency. The ripple like plot on the upper left and passband ripple. The ripple on the bottom right is the stop band ripple. Okay, like this too, the graphically it is identified. Yeah, the Parks-McClellan algorithm is is implemented. Yeah, is implemented using the following the steps. Step 1, initialization. Choose an external or extremal set of the frequencies. So that is omega I power 0. So finite set approximation. Calculate the best Chebyshev approximation on the present extremal set. Given the value delta of m for the mini or max error on the present extremal set. Okay, this is the implementation while using the solve steps. Step 1, it is involved the omega I power 0. Our second step is, so we have to set that all values, giving that value delta of f power m for the mini max error on the present external set. Coming to the third step, interpolation. We have to calculate the interpolation. Calculate the error function E of omega over the entire set of frequencies. Omega using that, with the help of that omega using the second finite set of approximation. It is also involved this, and looks for local maxima of e power m mod e power m of omega on the set omega. Okay. Now coming to the fifth step, if the maximum epsilon that e power m of omega greater than delta of m, then they update the external set to omega e power m plus 1. It is specified. Easily can compare the step 1 and step 5. So by picking new frequencies where e power m into omega has its local maxima, make sure that the error alternates on the order set for the frequencies as desired as per the step number 4. The step number 4 looks for the local maxima of e power m of m omega on the set omega. Okay, next coming to the fifth step, here the fourth and fifth return to the step 2 and iterate. How it is iteration values are displayed, how we are measured, how we are determined this all step by step procedure. Why we are following these all steps? Because of that FIR non-recursive filter optimum things. While using this previous methodology, we are unable to expect that that optimum response. That's why we have followed this particular algorithm, Parks-McClellan algorithm, for implementing these all steps, 5 steps. Next step is, if maximum this value, then the algorithm is completed. Use the set omega I power 0 and the interpolation formula to compute an inverse discrete Fourier transform to obtain the filter coefficients. Yeah, the Parks-McClellan algorithm may be restated as the following steps. Because of our expectation is should be optimal. Okay, so first you can take that make an initial guess of the L plus 2 extremal frequencies. Second one, compute delta using the equation is given. Okay, third one, using the law Lagrange interpolation, we compute the dense set of samples of a power of omega, a into of omega over the passband and stopband. You're coming to the fourth step, determine the new L plus 2 largest extrema. And coming to the fifth one, if the alternation theorem is not satisfied, then we go back to the step number 2, that is compute delta using the given equation, and iterate until the alternation theorem is satisfied. If it is not satisfied, again you can follow these all steps, previous one and this one. We will expect this desirability. Yeah, next coming to the sixth step, if the alteration theorem is satisfied, Then we compute impulse response, that is followed by h of n, and we are done. So finally, to gain a basic understanding of the Parks-McClellan algorithm, mention all above steps. Okay, we can rewrite the algorithm above in a simpler form as guess the position of the extrema, or what you call evenly space in the passband and stopband. Okay, so of that we will export that all performance levels. Yeah, they perform polynomial interpolation and re-estimation position of the local extrema. Okay, finally move to extrema to new positions and iterate to until the extrema stop shift. Okay, like this we should follow. Okay, by using this, so by using this output response, we will export the right display the various extreme frequencies of the plot shown. Already we have verified the extremal frequencies are the maximum and the minimum points, the stop band and the pass bands. The stop band ripple is the lower portion of the ripple on the bottom right of the plot, and the pass band ripple is the upper portion of the ripples on the what you call top left of the plot. So the graph is available, already we have verified. We have to consider the same graph. Easily can analyze this all. We will ready to interpret this all. The dashed lines going across the plot indicates the delta or maximum error. So given the position of the extremal frequencies, there is a formula for the optimum delta or optimum error. Since we do not know the optimum delta or the exact positions of the extreme on the first attempt, we iterate. This all easily can interpret by using this output response of the Parks algorithm. Okay. Effectively, we assume what do you call the positions of the extrema initially and calculate delta. We then what you call re-estimate and move the extrema. Like that, we should follow this all step-by-step procedure and calculate the delta or the error. We repeat this process until we will ready to expect the delta value. Stop the changing. The algorithm will cause the delta error to what you call converge, or generally within 10 to 12 iterations. Okay. So using this all interpretation, we should follow this all what you call using this all MATLAB software. Easily can verify that expected thing. Okay, by using the MATLAB software. Okay, we should write that a piece of code. Okay, using this all piece of code, we will export that all optimum response. From that, so that a built-in function FIR-PM, that is a Parks-McClellan optimal FIR filter design. So that is syntax is followed by where B is equal to FIR-PM of n comma f comma a. B is equal to FIR-PM of n comma f comma a comma w, where B is equal to FIR-PM of n comma f comma a, f type, and where B is equal to FIR-PM of n comma f comma a, L grid. Okay, of that B comma error, it is a FIR-PM. Of that, should write that all a piece of code B comma error with the rest and FIR-PM. Okay, so use this where B is equal to B is equal to FIR-PM of n comma f comma frequency SPPW. Okay, where B is like this. Go on writing that, we will expect that all. Yeah, if it is B is specified, it is written now vector B contains the n plus 1 coefficients of order in non-recursive filter like FIR filter. The frequency and amplitude characteristics of the resulting filter match those given by the vector f and a. Okay, like this, we can write this according to this, writing the piece of code like this, where b is specified. So we're going to weight the frequency bins. After that, use the filter type specified to the FTY, and use the integer what you call grid to the control the density of the frequency grid, and return the maximum ripple height in the error. You can use this with any of the previous input syntax. Okay, by return this frequency response characteristics as structure. We will expect that all. Okay, FIR filter whose frequency amplitude characteristics. Okay, best approximation. The response returned by the function handle frequency response. So where if you are using this, design the anti-symmetric odd filters. Okay, after that, where f type specific that a filter has that differentiator or Hilbert transform. Like this, if you do not specify on a f type, a call made to the frequency p to determine. Okay, so like this, the default symmetric property either is satisfied or not. Graphically, you have to verify. Okay, like this, we are done. We will do the number of problems using this optimum algorithm with effect with particular image approximation and so on.
Like, share and subscribe. Hit the bell icon for more updates.